Okay, in this video we're looking at conservation of energy of a simple harmonic oscillator. We have no dissipative forces, so all of our energy is going to remain mechanical. We're told that we have a spring constant of 435 newtons per meter, and we have an attached mass to that spring with that spring constant that weighs 2.6, or rather has a mass of 2.6 kilograms. We are told the initial amount of elastic potential energy, the initial stretch of the spring, and we are told the initial amount of kinetic energy when the system starts at t equals 0. So if we were to draw a picture of the system at t equals 0, what that would look like is something like this. Okay, so imagine, right, here we have our ground, and we're going to have our spring. Okay, here's our mass. Okay, and there's a non-zero initial velocity. Okay, so we have v naught, okay, not equal to 0, because otherwise we would not have kinetic energy to start with. And then we also have some stretch, so we also have a force. Okay, so this is F naught, the initial force associated with that initial stretch, which we could find using the spring constant and Hooke's law. Okay, so we were asked for the resulting amplitude of the oscillation. All right, so we can find that by using conservation of energy. Okay, so using conservation of mechanical energy for our oscillator here, our simple harmonic oscillator, we have that the total energy is going to be equal to 1/2 k amplitude squared, right? Because that's when all the energy is elastic. It's also equal to 1/2 m v max squared, and that happens at equilibrium when all of the energy is kinetic. And then it's equal to anything in between, so 1/2 k x squared plus 1/2 m v squared, where x and v are anything that are not maximum amplitude or maximum velocity. Okay, and then I just want to show the direction of positive x. We'll define it in this way. Okay, and all right, I was just going to point out that this is at maximum extension or compression, and this here is at equilibrium. I just wanted to point out the locations where they occur. Okay, so in this problem, we are told that we start with a certain amount of energy. I'm going to call this total. Okay, so we're told that the starting energy is a combination of kinetic and potential. Specifically, we are told that we start with 10.5 of potential energy, so 10.5 joules of potential. And remember that 1/2 kx squared is potential energy, and 1/2 mv squared is, by definition, kinetic energy. Okay, so that's our potential, the 10.5. Then we also have the 15.9 joules of kinetic energy. Okay, excellent. And then we want to use that to find the amplitude. Well, since we know that the total energy is also equal to 1/2 k a squared, then we can simply, since we know k is given as 435 newtons per meter, like so, we can then solve for amplitude. Okay, so let's take our values here, our 10.5 plus 15.9. So 10.5 plus 15.9. All right, so we have 26.4 joules on the left-hand side of the equation, and that's going to equal 1/2 435 newtons per meter amplitude squared. So we'll go ahead and start solving for amplitude here. So we're going to have 2 times 26.4 joules. Okay, and that's going to be divided by 435 newtons per meter, all inside the square root. Okay, and it's important to point out that symbolically, what we're looking at here is that amplitude is just equal to 2 times the total energy divided by k, all inside the square root. All right, I'll make this show up on screen. Okay. All right, so then we'll go ahead and get a value for amplitude. So I'll take our square root. Okay, and 2 times that value there, which doesn't have any rounding in it, so I guess we could have retyped it, but that's fine. And 435. Okay. All right, so we get an amplitude of 0.348. We're working with 3 sig figs here. Yep, so 0.348 meters, 34.8 centimeters. Okay. So that is the amplitude of the oscillation, as what we're asked for in part A. In part B, we are asked for the resulting maximum velocity of the oscillation, and we'll use a quite similar technique. We're simply going to relate the total energy to 1/2 mv max squared. All right, I will leave it symbolic this time, rather than just doing it as a side note, and show you then that if we solve for v max, it's going to be 2 times the total energy, and then divided by the mass. Okay, so quite similar to the concept of 2 times the total energy divided by the spring constant in order to find the amplitude. Okay, so numerically, what that looks like in this particular problem is going to be 2 multiplied by 26.4 joules, all divided by the mass, the attached mass, which is 2.6 kilograms. Okay, and that will give us our maximum velocity. So we're going to have, I'm going to go up here because it's quite similar. The only difference is instead of dividing by 435, we're simply dividing by 2.6. All right. All right, so I get a maximum velocity of 4.51 meters per second. Okay. So it's, what else, that's it for the question, for the problem. I do want to do one extra part here, right? So we'll say additional information. And we'll call it an additional question, in fact. I just want to say, well, what is the position function of the oscillator? Okay. I'm going to do some resizing here. So to answer that question, and the reason I want to even ask it in the first place, is I want to show that this position function would neither be described completely by a cosine nor a sine, because we're starting with both non-zero stretch, right? So non-zero force, and we're starting with non-zero velocity. So we're starting with, as the problem states, both potential and kinetic energy. So let's then see, we've solved for some key information. We can also solve for omega, right? So we already know that the amplitude is 0.348 meters. Omega is simply going to be the square root of k over m, okay? Yep. Let's see, yep. Okay, and so that's going to be the square root of 435 newtons per meter divided by 2.6 kilograms. So let's go ahead and get a value for that. All right, so 435 divided by 2.6. Okay, so we get 12.9 as our angular, not velocity, but angular frequency, radians per second. So there we go, 12.9 radians per second. Okay, and so then the form, all right, our position function is going to take the form a cosine of omega t plus phi, because we have to acknowledge that we're not starting at maximum stretch, because cosine with a phi of 0, and I'll say because phi equals 0, only when system starts with velocity equals 0. But it's definitely not the case. We're starting with non-zero velocity. And in fact, we can find out exactly how much velocity we start with. So let's, and that's which, we can think about it that way. I'd say a better way to think about it is just think about the initial stretch. Because the reason I say the initial stretch is because then we can set t equals 0 and say at t equals 0, this is where the object is located. So I'm going to say at t equals 0, x of 0 is going to be a times cosine of omega times 0 plus phi, which is just going to be a cosine of phi. And that's going to equal, well, it's going to equal the location at x equals 0. But how do we know the location at x equals 0? Well, we know it using conservation of energy. We can solve for the exact location. Okay? Okay, so I'm going to tell that x naught. And we have, we've got our total energy. So we've got E total is going to be 1/2 k x naught squared, right, with our initial potential energy, plus k naught, the initial kinetic energy. All right, and we're given that. And then so just to point out that this right here, this whole expression, is just PE naught, the initial stated potential energy. Okay. So then we plug in what we got. We know that we have 26.4 joules over here. We've got 1/2 times 435 newtons per meter times x naught squared, and then plus our initial kinetic energy, which 15.9. Okay, so 15.9 joules. Okay. So then we're going to have 26.4 minus 15.9, which, well, obviously is just the initial potential energy. We could have even saved a step there because it's just obviously going to have to be 10.5. Okay? So then we're going to have 10, and I'll also show you what I'm doing here. So this is E total minus KE naught. Make that a little bit clearer. KE naught, in fact, is simply equal to PE naught. All right, the initial potential energy, which is just going to be 10.5 joules, right, which we could have simply gotten from the problem itself. Okay, and then that's going to be equal to 1/2 k x naught squared. So then x naught is going to be the square root of 2 times PE naught divided by k. All right, so that's going to be 2 times 10.5 joules divided by 435. Okay, so let's see, where do we start? All right, what's our initial position? All right, let's open up another square root here. All right, so 2 multiplied by 10.5 divided by 435. All right, 0.220. 0.220. Okay. All right, and just going to do one other quick resize as we're running out of space. There we go. Okay, and that's meters. Okay, so now we know that's, and also it's good to compare that to our amplitude because it better be smaller than our amplitude. And sure enough, 22 centimeters is smaller than 34.8 centimeters. Okay, and so that's our initial stretch, initial extension. So now we can finally solve for our phase angle because we know, so I'll say thus, okay, 0.348 meters, which is just amplitude, times cosine of phi equals 0.220 meters, which then tells us that phi is going to be cosine inverse of 0.220 divided by 0.3480. Meters cancel. All right, and let's get that angle. And we'll finally have our position function, our additional question. Okay, so I'm going to go ahead and do an inverse trig function here, cosine inverse. And we're going to, and we could have, chosen a different phase angle here, right? We could have based our position function off of sine instead of cosine, and we just would have had a different, different phase angle, because that's all this is. It's just an offset. It's just shifting our function that describes the motion to the left or the right with regards to time. Okay. But anyway, let's plug in our values here. So cosine inverse, I need this value in the numerator, and I'm going to be dividing it by the amplitude that we saw for up here. All right, so now we definitely want our unrounded values here. Okay. Okay, and that probably is in the wrong mode. So let's, yeah, it's in radian mode. Okay. So now I have in degree mode. Do the same thing. Okay, 50 degrees. All right, 50.9 degrees. 50.9 degrees. So finally, we have that our function of time, our actual position function for this oscillating system, is 0.348 times cosine of 12.6 radians per second times time plus, well, actually, I do want it in radians. It would have been a bad idea. I put it in degrees because I always think about things in degrees, but we absolutely want it in terms of radians because we have our, our velocity here, or rather our frequency in terms of radians per second. In fact, the whole function is based on radians. That's true of all oscillators and waves. So here we absolutely want our phase angle as 0.88. Okay. All right. So 8, and then 888. Look at that. All right, and that's radians. Okay, all done. All right, there is our final answer.